Hello viewers, in this video we are going to discuss B plus tree indexing method under tree structured indexing techniques. This lecture is focused on discussing these points. One is what is B plus tree, what are the properties of B plus tree, what is the format of index nodes and leaf nodes, and how the basic operations such as search, insert and delete operation takes place in B plus tree with suitable examples in this lecture. B plus tree is a dynamic tree structured indexing method that allows records to be accessed either sequentially or randomly. That's why it provides efficient support for range search as well it provides support for equality search. Okay, because the technique which allows records to be accessed sequentially, they support range search. And if they support uh, records to be accessed in random search, obviously it supports for equality search. Okay, so B plus tree, since it allows records to be accessed both sequentially as well as randomly, it provides support for range search as well as equality search. Okay, and the another important point in B plus tree is that the actual records are stored into the leaf nodes in sorted order. Okay, and index entries are stored in leaf nodes. Okay, and inside the leaf nodes, actual records never be stored. Only index entries are stored. And in leaf nodes, references to the records also shall be stored. Okay, and this method is known as a dynamic method or self-balancing method because it gracefully adjusts to the changes in the file. Okay, even if we perform multiple insertion or deletion operation, B plus tree gracefully adjusts its height, number of nodes in the tree and entries in the leaf node as well as index nodes. Um, that's why since it adjusts on height, number of nodes and entries in the nodes, it is known as self-balanced method or dynamic method. Let us now discuss the properties of B plus tree. There are two important properties all B plus tree must maintain. First important property is B plus tree must be a height balanced one. Height balanced meaning is the distance from root to all leaf nodes must be same. In other words, number of links from root to all leaf nodes must be same. In such case, the tree is known as height balanced one and B plus tree always must be a height balanced one. And the second important property is minimum 50% occupancy must be maintained in all index node as well as page node except the root node. Minimum 50% occupancy means at least it has to be at least half filled. If suppose the node size is 4, what is the half 50% occupancy? Minimum the node must have 2 entries. Okay, 2 entries must be filled into that. So this is the important property that need to be maintained in all nodes of the tree. Okay, and this minimum 50% occupancy is applicable for each index node and a page node. Page node means leaf node. Okay, and it is not applicable for root node because for root node the minimum occupancy is 1. Okay, so let us discuss this point in detail. Okay, each and every index and page node must contain m number of entries, where this m number of entries always greater than or equal to the half node capacity, that is represented as D parameter, and this number of entries always must be less than or equal to 2D. Okay, D stands for half capacity, right? 2 into D, it indicates the full capacity. Okay, always the number of entries which are kept in the nodes of B plus tree, that should be greater than or equal to half node capacity or is less than or equal to its full capacity. Okay, and this half node capacity or its D is also known as order of the tree. Whereas coming to root index node, it must maintain the number of entries in the root node must be greater than or equal to 1. The minimum capacity required for root node is 1 and maximum is up to the full capacity of the node. Okay. So let us discuss the format of nodes. Coming to leaf node must contain actual records or else just references to the records on data pages. And all leaf nodes must be connected to form a doubly linked list. Okay, coming to non-leaf nodes must contain m number of search key values and m plus 1 number of pointers, where from this you can understand each and every index page must contain one pointer more than the number of keys. Okay, so you can observe in this node here m number of search key values starting from 1 to k1 to km, right? So there are m number of search key values and m plus 1 number of pointers because it starts from p0 to pm, right? So there are m plus 1 number of pointers. Okay, and the entries which are pointed by the left pointer of any search key value always be less than the search key values. Okay, the entries which is at the right hand side of the search key value always pointing to the node having the values less than or equal to, always pointing to the entries having the values greater than or equal to search key value. Okay, so that's why each key in non-leaf node serves as a separator for the contents of the pages pointed to by the pointers to its left as well as right. Let's now discuss the structure of B plus tree. In B plus tree, all the nodes are arranged in hierarchical order where each node represents the memory page. Okay, and in leaf pages, all actual records are stored and those records are sorted by search key value. Okay, then since each node is equivalent to one memory page, these leaf nodes or leaf pages are leaf nodes also called as leaf pages. And since leaf pages contains actual records, they are also called as data pages. And coming to non-leaf nodes, it always contains index entries. Okay, that's why these non-leaf pages are known as index pages. And here you can notice the tree is a high balanced one. That's why first property is maintained. And also you can assume that all nodes are having minimum 50% occupancy, and maybe root node also may have, it also might possess the property that is minimum one entry must be available in the root node. Okay, and here you can notice all the leaf nodes are connected with doubly linked list. So with the help of this doubly linked list, the entries can be accessed very easily, moving from one node to another node in the leaf of the tree is very easy. Let us now discuss one example B plus tree. Here in this example B plus tree, this is the root node and these are the leaf pages. In leaf pages you can observe all actual records are stored, and in the index node only index entries are stored. And in leaf node you can observe how we can say in this leaf node actual records are stored. Here you can notice all the entries are having search key value followed by the star mark. Here star mark indicates the presence of the actual record having the search key value too. In addition to that, all the other fields also included. So in order to represent the tree in a simplified manner, instead of keeping the entire record, all the fields in the record, the star mark is specified in order to simplify the representation of the tree. Okay, so 2 star indicates the record having the search key value 2, and also the other fields also present. That is what the meaning. Okay, and here coming to the index node, here the left pointer of every search key value pointing to the node having the entries less than the search key value, and right pointer is pointing to the node having the values greater than or equal to the search key value, and you can notice that that is applicable for all the entries in the leaf node. Okay, so you can notice this in this diagram, and you can see the two important properties are possessed in this. Here, the node size is 4, right? So minimum occupancy in every node is minimum 2. Here 4 occupancies 4, here 2, here 3, and here 4, here also 4. So minimum occupancy is maintained in every node, and also it is high balanced one. So this given B plus tree, since it possesses both the properties, it is a perfect B plus tree. Let us now discuss how search operation is performed in this example. Especially, we are going to discuss how equality search operation is performed. Okay, and so now we are going to search for the record having the search key value 5. So since we are searching for the key equivalent to 5, since equal operator is used, the search operation is known as equality search. Okay, so the search operation starts from the root and the comparison is made with the search key value. First here 13. Since 5 is less than 13, the search proceeds to the left pointer of this search key value, and we can find the record in the third place having the search key value 5. Now this record can be accessed and sent as the output to the user. Okay, and coming to the range search, in this example we are going to find out the records having the search key values between 14 to 20. Okay, since we are going to retrieve the records between the range of 14 to 20, it is known as a range search. Okay, so very similar to the previous search, here also search operation starts from root node, and when we make the comparison with 13, first we have to take the minimum value and make comparison with the search key values in the root node. Okay, so when we compare this with 13, this 14 is greater than 13 and less than or equal to 17. That's why the search proceeds to the right pointer of search key value. So okay, so we come to this node, and here the first record is having the search key value 14, and our minimum value is also 14, right? So it proceeds, the access continues up to 20, and when it comes to 22, this is search key value is greater than 20. So up to this 20, all the records can be accessed, and here the access can be proceeded from this node to this node, because these nodes are connected with W linked list, so it can easily move from this node to this node. So since this linked list is present in the B plus tree, it helps to access the records sequentially whenever range search is performed. This is the major advantage of having the linked list between the leaf pages. Let's now discuss the procedure that is used for performing insert operation. Very first step, we have to find out the correct leaf node into which the record need to be inserted. After finding the leaf node, put the data entry into the leaf node if enough space is available. If there is no space available, then we have to split the node into two, let it be L and new node L2. And after splitting, redistribute entries evenly and copy up middle key. And insert index entry pointing to L2 into parent of L. Okay, and these steps happen recursively. And coming to the split of index node, redistribute the entries evenly but push up middle key. So this is very important point. Whenever index node is splitted, after redistributing the entries evenly, middle key need to be pushed up. Whereas coming to the split up of leaf node, after redistribution of entries, middle key need to be copied up. Okay, so these two are the major difference. Let's now discuss how to insert a record having the search key value 8 into the B plus tree. Um, so at starting, we have to compare the search key value with the search key values in the root node, right? So when we make the comparison, 8 is less than 13, so we proceed with the left pointer. And when we come to this node, it is already completely filled up. So there is no space for inserting the record having the search key value 8. So when there is no space during the insertion operation, what we have to do? We have to split up the leaf node. When we split up, we will be having two nodes. In the first node, we will be having the entries 2 and 3, and in the second node, we will be having the entries 5, 7, 8. Okay, you can notice here. So whenever we split up it, we will get like this two nodes. Okay, first node is filled up with 2 and 3, second node is filled up with 5, 7, 8. After split up and redistribution of the entries, the middle key need to be copied up. Since we split up the leaf node, the middle key need to be copied up. Okay. So when we copy up the entry, it need to be inserted into the index node. Since there is no space in the index node, again we have to do the split up processing index node also. And here one thing we need to notice is that whenever we do the copy up operation, the middle key present in both leaf node as well as the index node. Okay. But since there is no space in the index node, we have to split up the index node into two. Okay, and in the first node, the first two entries will be there. In the second node, the entries followed by the middle key will be there. So when we split up, we will get the nodes like this, and entries will be redistributed like this. After split up and redistribution, what we have to do? When we split up the index node, the middle key need to be pushed up. The middle key need to be pushed up. Here you can notice whenever we push up the middle key, the entry exists only in the parent node, not in the child node at all. Okay. Okay. Then now this single node, after split up, it becomes two nodes with one parent node. So now this node need to be replaced with this structure. So now you can see when it is replaced with these nodes, now the tree becomes like this. Okay, the point is also adjusted. You can observe entries pointed by the left pointer all having the values less than the search key value, and all the entries pointed by the right pointer are having the values greater than or equal to the search key value. You can notice this one in every node. Okay, and now this tree is a B plus tree because it possesses the both the important properties. Now you can see the tree is the high balanced one, and in every node minimum 50% occupancy is maintained, and in root node one occupancy is there. In other nodes here two occupancy, here two, three, two, three, three, three. That's why since both the properties are maintained, now it is a perfect B plus tree. Now this B plus tree, it self organizes itself whenever we do the insertion operation. That's why this method is known as dynamic method. Okay, let us now discuss how to perform insertion operation with the redistribution method. Okay, and whenever we try to insert a entry into a node, and when there is no sufficient space, before splitting up the node, its entries are redistributed with its sibling. Okay, according to redistribution method. Okay, so what does mean by sibling? Sibling is a node that is immediately to the left or right and has the same parent. Okay, it has to be immediate left or right node. So in such case, it is known as sibling. Okay, and the advantage of redistribution is that it improves the average occupancy in B plus tree. That's the major advantage. Okay, let us now try to insert the record having the search key value 6. So when we compare this one with this search key value in the root node, it is less than 13. So we proceed with the left pointer, and when we come to this node, there is no space at all. So now we try to insert the record with a redistribution method. So when we try to insert 6 supposed to be here, so 2, 3, 5, 6, but there is no space for 6 now where 7 exists. So, but when we look at its sibling, it has space. That's why we can move this record having search key value 7 into this sibling, and we can place the record with 6 search key value. Okay, so when we do this, this 7 will move here and 6 will move here, and after doing this, we will get the resultant tree like this. So 6 is inserted into this, and the 7 which was already in the left node, now it is moved to the right, its sibling, and you can notice here, and after redistribution, its search key value also must be updated accordingly. Here, the first entry in the right node must be placed as the search key value in the index node. Okay. So now you can observe after this insertion, both the properties are maintained. Now the tree is the height balanced one, and every node is no every node is having minimum 50% occupancy. Now discuss how distribution and merge operation takes place when we delete a data entry from B plus tree, and if there is no minimum occupancy is maintained. So coming to redistribution, we have to redistribute entries between the node and its adjacent sibling. And after redistribution, we have to update the parent to reflect the redistribution. That is, we have to change the entry pointing to second node to the lowest search key value in the second node. This is very important. Okay, and coming to merge operation, merge the node with an adjacent sibling, and after merging, update the parent to reflect merge by deleting entry pointing to the second node. Okay, and if last entry in root is deleted, the height of the tree will be decreased by 1. Okay, always merge could propagate to root, that's why it decreases the height of the tree. Let's now discuss the procedure that is applicable for deleting a data entry from B plus tree. So this procedure starts at root, and making the key comparison, it finds the correct leaf node where the entry belongs. After finding the leaf node, we can remove the entry. If the node is at least half full after deletion, it's fine. Otherwise, if the node is not at least half full after the deletion operation, we have to try to redistribute it by borrowing from its sibling. Okay, and if redistribution also fail, then we have to merge the node and its sibling. Okay, if merge occurred, we have to must delete index entry pointing to the node or sibling from the parent of the node. Okay, let's now apply the procedure into this tree. So first we are going to delete the record having search key value 19. So first when we make the when we start from root, when we make the comparison, this 19 is greater than 17, so we follow this right node, right pointer. Then coming to this node, 19 is less than 24, so we come to the, we reach this node. Okay, when we reach this node, we can find the record. So now it can be deleted. So after deletion, this node maintains minimum 50% occupancy. What is the size of the node? It is 4. So what is the minimum occupancy? 2. So after, even 19 is deleted, it maintains 2. So it can be easily deleted. But when we try to delete the record search key value 20, so we follow the same path. But when we try to delete it, this node now it has only single entry, so which is less than minimum occupancy. So how can we handle it? By borrowing one entry from its sibling. Okay, so now 24 can be borrowed from its sibling to here, and now if you look at the sibling also, even after giving this 24 to this node, it will be having 2. So it maintains minimum occupancy. So after redistribution, its parent node must be updated, right? So the parent node, now it is having 24, right? It has to be replaced by 27. Okay. So now the resultant B plus tree, it looks like this. Okay, here you see now this node is having 22 and the borrowed entry 24. Both are here in this node, and this node is having 27 and 29, and the parent node is also updated with the first entry in the second node. Okay. Now you can notice that both the properties are maintained. It is the tree is the height balanced one, and the minimum occupancy 50%. That is, minimum two entries are there in each and every node of this node. So like this, a B plus tree, it self organizes itself, um, uh, even after number of insertions as well as delete operations. Let's now discuss the deletion of entry having the search key value 24 from this B plus tree. When we try to delete it, no, when we start the process from root node, since 24 is greater than 17, we follow the right pointer. And when we make comparison, 24 is less than 27, right? We follow the left pointer of this. And we end up in this node. And when we try to delete this record having search key value 24, and this node loses its minimum occupancy. So what we have to do for handle this, we have to borrow an entry from its sibling. So when we try to borrow entry 27 from its sibling, it cannot be done, because when it gives it, it will lose its minimum occupancy. That is, it will be having only 29 as its entry. So it is not possible. So how can we handle this? So only possible way is we have to merge these two nodes into a single node. Okay, so we have to merge these two nodes into a single node. When we merge it, these two nodes, it will become a single node. It will be having 22, 27, 29, because 24 is going to be deleted, right? So these three entries will be in single node. This node, it is as it is. And also this entry in the root node, which is pointing to the second node, need to be deleted. Okay, so we have to delete the entry from its index node. So when we delete it, this index node will be having the only single entry which is less than minimum occupancy. So since it loses its minimum occupancy, how can we handle it? We have to merge this node with its sibling. Okay, what its sibling? What are its entries? 5 and 13. So when we merge it, here in this level only one node will be there. So so there is no need of having the root node. So let us pull down this 17 into this node. So when we pull down this 17, the root node now it will be having 5, 13, 17 and 30, because 27 need to be deleted, right? So now root node it will have 5, 13, 17, 30. So now the final B tree, it will be having these nodes. There is no changes at all, and this node it becomes like this. Okay, so here you see after after merging of these two nodes, it becomes a single node, and this node is as it is. There is no change in these nodes, and the root node it becomes. It will be having 5, 13 and 17 and 30. So this is the final B plus tree after deleting a record 24 with the redistribution method. Okay. Students, in this video we have learnt about a B plus tree, its properties, and how to perform insertion, deletion and search operations with suitable examples. If you find this video useful to you, kindly subscribe this channel. Thanks for watching.